Okay, welcome to our next section for chapter 19. We'll introduce the third law of thermodynamics, and that is going to center again around entropy, but this lays the groundwork for how we can calculate and apply numbers to entropy. We need to set a ground floor, or a grounding, or a starting point, a baseline for entropy values, and that's what our third law of thermodynamics does for us. And the third law says that the entropy of a pure crystalline substance at absolute zero is zero. You can see in the diagram on the left. At absolute zero, a perfectly organized crystal structure has a value for entropy. But that means that in reality, we can never achieve those conditions. We never can get down to absolute zero, and we can never have a perfectly organized crystal structure. So that means every compound, every molecule, every atom has an entropy value greater than zero. Some value greater than zero. Okay, and that allows us to calculate and set values for entropy. So entropy values are standard values. So each compound or atom has a standard entropy value, and we can look those up. Those are in the appendix in OWL. You can find those right with your other thermodynamic data, your entropy of formation data. It's all in the same place. So we just look up entropy values for various compounds and atoms. So here's a brief list of what we see here. Notice the units again on entropy are joules per mole per degree Kelvin. Right, so the units are a little bit different. And also keep in mind that for enthalpy values, delta H values, those are typically reported in terms of kilojoules, where entropy is in just joules, 1,000 times smaller. So there's a difference in our units when we do that, and we'll start combining enthalpy and entropy in later sections. So I'll have to just please be aware of your units that you're working with. So standard entropies, as you can see, tend to increase with molar mass, because now we have a larger molecule, more atoms involved, more microstates, so you end up with a higher entropy value. And we see larger and more complicated molecules have higher entropies. We can see our three basic organic molecules, methane, ethane, and propane, and we go from small entropy values to larger. These are all gas phase molecules at room temperature, so they have relatively high entropy values, but because I've got more atoms involved, I can draw more microstates. I can place energy on specific atoms within a molecule. So more atoms present, more microstates that I can draw, higher entropy values. So what we're really interested in is an entropy change. Because again, in order to determine if a process is spontaneous, we're looking at the entropy change for the universe. So I need to be able to determine what the entropy change for a reaction is. Right? And that's really simple. It's the same equation that we used back in Chem 111 in chapter 5 in our thermochemistry chapter when we calculated delta H values. It's delta S for the reaction is equal to the sum of the entropies for the products minus the sum of the entropies for the reactants. Right? And that's all it is. And again, this is the exact same equation that we used to find an enthalpy of a reaction. Our delta S values are just table values. And what is different, the one thing that's different for entropy compared to enthalpy when we do this, for pure elements, we always have an entropy value. The value is never zero. But when we calculate a delta H, our delta H of formation for pure elements, for elements in their naturally occurring states, is zero. So our enthalpy of formation for hydrogen gas or chlorine gas or O2, those values are zero. Right, so that is the only difference in the process and how to calculate this. But the delta S of the reaction is calculated the exact same way as delta H for the reaction. Right. So let's use standard conditions and let's calculate the entropy change for reactions. Right. So here's a table with some values. Take a minute and go ahead and try your hand at calculating the entropy change for this reaction. Right. Hit pause, and when you got an answer, let's start up again and we'll go through and we'll see how you did. So we set up our reaction, and notice I set this up, the entropy change for the reaction is equal to the sum of the products. So I only have one product, I have NO2, but I have two of those, so I need to use my coefficient in my balanced equation. So my coefficients absolutely apply. So it's 2 times 240. That's the entropy change for my reactants. And on the product side, on the reactant side, excuse me, it's NO and oxygen. So I again apply my 2 coefficient for the nitrogen monoxide, so 2 times 211, and my reactant for oxygen is 205. So for my products, that's 480. For the reactants, that math combines to 627. So the delta S for the reaction is negative 147. And again, my labels are joules per Kelvin per mole. So what does this mean? Did I gain or lose entropy? Right? Entropy has decreased. I have a negative value for my delta S. But why? If we look at this reaction, what factors would tell us ahead of time that our entropy value should decrease, needs to be negative? And it's because everything's in the gas phase, so phases don't matter. That's the first thing we want to look at. If we're changing phases, if we're going from a gas phase to a liquid or solid phase on the product side, that would be indicative of a loss in entropy. But in this case, we have more moles on the reactant side. So as this reaction proceeds, I'm producing fewer moles. I'm going from 3 moles worth of reactants to 2 moles worth of products. Fewer particles, fewer microstates, less entropy. So again, these microstates all apply. So when you look at a reaction, you can ID ahead of time. You can qualitatively determine the sign of the delta S of the reaction, positive or negative, just by looking at any potential phase changes that are occurring and the number of moles that are involved. Right? And if we're decreasing the number of moles by a fewer moles on the product side than on the reactant side, I know my delta S value has got to be negative. That will never vary. Right? Here's another question for you to work on. So try this. This takes what we just did and adds another level of complexity to it. So hit pause and take a couple minutes on this one. All right. So same reaction that we just did. So I know my delta S value has to be negative because I'm going to fewer number of moles of products. So we know that. So we're going to do the exact same thing to start. I need to calculate my delta S for the reaction, and then we're going to consider the specific amount of nitrogen monoxide. Okay, I don't need to deal with that until the very, very end. So the beginning is exactly the same thing. Products minus reactants. So I set up my values 2 times 240.1 minus 2 times 210.8 and 205.1. Right? That gives me my delta S of negative 146.5 joules per Kelvin per mole. But now, because my question is specifically talking about nitrogen monoxide, it's not per 1 mole of NO. I have 2 moles of nitrogen monoxide for my balanced equation. So I change my denominator to talk about the specific compound that the question is asking about. And when I do that, I need to include any coefficients from my balanced reaction. So the delta S for this reaction is a loss of 146.5 joules per Kelvin for every 2 moles of nitrogen monoxide. So when I want to calculate just the amount of energy for this reaction based on 1.79 moles, I simply take that delta S R that we calculated and multiply it. Because I need to get rid of that mole term. And that's all I need to do. So basically this is minus 146 divided by 2 times 1.79 or negative 131.1 joules per Kelvin. And if you're not really sure about how to do that, let the units guide you. If we know that entropy values are given in the table as joules per Kelvin per mole, and my options for my answer are just joules per Kelvin, I know I've got to get rid of that mole term. And to do that, I simply multiply my standard values, my delta S values, by moles, and that removes the mole term. Okay. And that's it for calculating entropy values. It really is very, very simple, and it's the exact same process for calculating delta H. And later on, we'll have some questions where we're going to need to calculate the delta H for a reaction, and we're going to do it the exact same way. All right, we're going to leave it here for part 3. We're done with introducing what our laws of thermodynamics are, and now we'll start applying them and doing some further calculations. All right, thank you very much, everybody.